So, hi. So today what I'd like to talk is the problem, mainly the problem of evaluating a classification model, which is generally considered not the most glamorous thing. People like to talk about the latest algorithm to do classification or whatever else. But practically, measuring the accuracy of a model is critical to deploy anything in production effectively. So, but practically, there are a lot of things that makes it harder. So what we'd like to talk today is about what are some of these challenges and how you can go about solving them. So in online retail, as you might know, there are a lot of classification problems. For example, one of them is, we have products, we need to place them in the right category so that they are displayed on the website in the right spot. And so we need to make sure that our classifiers are working as we expect them and correctly. So to measure the accuracy of a classifier, generally you need labels. So you need to have a set of experts that look at an item and provides you with the correct label for that item. And then doing that is generally expensive, right? Editors are expensive, or even if you use the crowd, running through a lot of items and collecting labels can be extremely expensive. And so using the labels effectively, it's key to run a production system and evaluate it correctly over time continuously. So the general approach that everybody should know, it's very simple. So let's say that you have a set of items that is that blue box. Think of it, if you're talking about retail, that could be your catalog of products. So you can have millions of products, and you have a model, the red circle, and that is producing estimates. So for each item in the blue box, you have an estimate, which is the tilde yi, and then out of this set of items, you want to measure how good your model is doing. So these items don't have a label, a true label attached to it. So you sample some of them. Let's say you sample n of them, and you run it through an editorial team, and you get the true label of it. And then you compare it with your model estimate, and you get an accuracy measurement out of it. It's very simple. So basically, you count how many you got right, divided by the n, the sample that you selected, and that's your number. That is pretty standard. The problem in practice is not so simple. And so let me tell you what goes on that makes it a little bit hard. So the major problem is this, is that your set of items, so let's say your catalog of products, it's not a fixed thing, right? So every day you get new products, some products get out of the catalog, and every day you ask to evaluate your model, to say, today on our catalog, our classifier is doing this well, and it's up to the standard that we require from it. And so this can be tricky, right? Because if the catalog is changing, the data that you collected yesterday, your labels are not valid today, at least not completely valid today. So you need to be careful about that. So the other major challenge is this, is that I oversimplified also the problem of evaluating the system, in the sense that you don't have always to evaluate the entire set, but sometimes people require you to evaluate, let's say, just the electronics part of your catalog, or the furniture part. And this is done daily. So every day you need to measure electronics, furniture, and then somebody comes in and says, oh, now I want to know how well you're doing on the whole catalog, right? So if you do things in the standard way, you end up collecting tons of tags, right? Because you look at electronics, you sample some tags there, measure accuracy, then you move to furniture, sample some more tags, and again. And so as you can see, you start collecting tons of labels, you run around into a lot of cost, and then when the time comes to evaluate on the whole system, what do you do with all these labels that you collected? If you're not careful, it can be very tricky. That brings me to the last point, which is, as you collect in label, it gets hard and tricky to reuse, and I'll show you an example, a simple example that shows how this can get pretty quickly out of N if you're not careful. Okay, so let me run through this simple example. So we start from the very simple case that I talked to you about at the beginning. So let's say that we have 1 million items that we're trying to evaluate our model on. So the standard approach is we sample 1,000 labels, let's say, just to give you a number. And I call that 1,000 label a budget, right? Because getting the labels for those 1,000 items, it's a cost. It costs you, the time of your editorial team, or the money that you spend on a crowd platform. And so that's why I call it a budget. So what you do out of it, you sample it randomly send it to the crowd, count how many times you got it right, and that's your measurement. So you divide it by 1,000, and that's your measurement. So what is the picture on the right? It's something that, to visualize what will going on later, and it's key that you understand what that is about. So on the x-axis, you have the products. So in this case, we have 1 million products. And on the y-axis, it's a representation of the probability which each item has been sampled. So given that we sample 1,000 products out of 1 million, we are sampling 1 product every 1,000. So that's why the probability is 1 in 1,000. And we're doing uniformly at random. So that's why the shape is sort of flat over the 1 million items. Okay, so that should be pretty straightforward. But it's important to understand what this means to be able to understand the example as it gets a little bit more tricky. Okay, so this is a simple case. You get the accuracy out. You're happy. You spit out your number, and we move on. But what happens the next day? The next day, we're going to have another, let's say, 500,000 items added to the set that you want to evaluate. So at this point, you don't just have 1 million, but you have 1.5. And as you can see in the graph, the first million has been sampled, 1 in 1,000. The remaining 500,000 is not sampled at all, right? So because we have not done anything. And what could be an approach to do accuracy? You say, forget about the new 5 million. I don't have time. I'm going to give you the number from yesterday, effectively. I'm going to use the same labels. I'm going to assume that the overall set of items is still sort of a similar distribution as before. And therefore, I'm going to reuse the same number. But as you can see, it's going to potentially give you a very inaccurate measurement. Now, practically, if your items are not changing all that quickly, that might be an okay solution. But generally, it's not a good thing. So the next approach is this. So we can say we have an extra 500 labels budget. Again, means that I can go out and sample 500 labels. So I'm going to do the same thing I did before. I use the 500 labels, sample uniformly at random. That's the blue box. So I'm sampling one item every 3,000 because I have a budget of 500. Okay. So again, it's done uniformly at random. So it's that blue box lower than the red one before. Then what I do is I take just the 500 labels, the new 500 labels, compute the accuracy, and that's my number. Okay. And that's correct, except that the previous 1,000 labels are sort of wasted. I didn't use them this time around. Okay. Now, in this case, it's pretty simple to understand how you should have done things. So the real way of doing things is that you should have sampled the 500 labels out of the new 500,000 products, right? And if you did that, that's the sort of profile, the sampling profile that you obtain. So you get something that is, again, uniform, but it's uniform over the previous sampling and the new sampling. Okay. And so overall, you took 1 item every 1,000, you collected globally 1,500 labels, and because you collect them uniformly, then you can use them all and compute the accuracy. Okay? In this case, if I did this, nothing got wasted. I really used my budget wisely. Now, what is the problem? That is not always so clean cut. So let's say, what if instead the budget was only 250? Now, you cannot do the same thing as before because your budget doesn't get you to sample enough the new 500,000 to get to a uniform sampling. Is that clear? So, but we can still try to make this work. So how do we do it? So we sample the 250 out of the 500,000 and we end up with that profile, right? So the blue box are the new 250 and they have been sampled 1 in every 2,000 as opposed to 1 in 1,000 of the red ones. And so when we then compute the accuracy, what we can do is weight differently what comes from the initial sample and the next one. And how would you do that? So because we sample half of the time items from the new 500,000 things, we need to kind of double the weight that we give to those items compared to the previous one. Okay? So the expression for accuracy in this case is a sort of a weighted accuracy. And so we compute the accuracy effectively on the first 100,000. And then we sum up the accuracy computed on the next one, the next 250 labels, but we give a weight of 2. That's why there's a 2 in front of the second part of that expression. And then we normalize by 1.5K because we counted twice the 250 labels. Okay, doesn't make sense. So the idea is very simple, is that because you sample less, half of the time, the labels, then you have to count them twice as much in your computation. Now, it's clear here that this is a nice example, it's simple. If in production, it becomes impossible to track these things manually, right? So you need to rely on a system that does this for you, because things can get pretty quickly out of hand. So as I said before, people might have sampled electronics, and means like they sample more electronics, then they sample furniture. And so the sampling profile can get pretty out of hand in no time. So what did we get from this simple example? So there's a simple approach that it's the one that you can always use, which is every time you need to do a measurement, sample uniformly, you're good, and just spit out a number like that, and it's okay. But as you can see, if you're gonna spend a lot of money potentially, especially if your items are changing constantly and if you ask to do a lot of measurement on it. Now, if you don't want to do that, there's a way to do it better, to sample more effectively, but that requires recording the sampling profile of the labels that were collected before. As you see in the example, to sample effectively the new batch, we need to know how we sample the batch before. And of course, if you have a sampling profile on your labels, to compute the accuracy correctly, you need to know how you sample them. So you need to have that profile available to do that. And as I said, unless you have a system that does this for you, it gets incredibly complicated very quickly. So there's a trade-off between how simple the measurements are versus the waste in money and budget to do the measurement. So one possible solution is this framework where at any given point in time, you not only collect the labels up to that point, but you collect also the sampling profile. So for each item, whether it was selected or not, you record the probability PI. So the probability at which it was sampled. It was a Bernoulli process with that PI. And you also record whether an item was selected for testing or not. And so effectively, you're storing that profile, that picture that I was showing. You're recording that picture. And then your accuracy is not the standard accuracy, it's an accuracy that follows that form. So every time you get something right, you count it, but you count it weighted by 1 over pi. And the reason is just as before. If you sample it less, you're going to weight it higher. And if you sample it more, you're going to weight it less. And then you need to normalize. So in front, there's an expression that normalizes this sum, so that you account for the different weights that you apply, just like in the example. So this is a sort of generic form of what I showed you before. Now, for this to be possible, it has to be the case that you sample each item, all of them, with a probability that is higher than 0. So in the initial example where we added the new 500,000, an accuracy measurement is not possible because the new items are not being sampled at all. Their PI is 0, and so you cannot do that. If you do this, though, you pay a cost to store this stuff, but you use all the time, all the labels for all your measurement, which is good. Now, just as a side note, this kind of approach is very tightly related to, oh no, sorry, I want to tell you another thing. So clearly, if the PIs are uniform, so basically if you obtain a uniform sampling profile, this formula is simply your standard accuracy measurement, nothing fancy there. And this kind of approach is very closely related to importance sampling. Specifically, this kind of measurement is usually called the self-normalized estimate, if you're interested. And all the results of importance sampling sort of have a parallel in this kind of framework here. Now, I didn't tell you, okay, how do we go about, if I record a probability sampling profile at a certain point, and now I have some extra budget, so I can spend more labels to get a better measurement or to be able to get a measurement. How do you go about doing that? So the key part here is that, and I cannot go into the math, but you can formulate this problem as minimizing the variance on your estimate, so minimizing the variance on the accuracy measurement, with a constraint on the budget. That turns out to be an optimization problem, and a nice part is that you can solve it efficiently. It's actually pretty easy to solve. And so you can spend your budget wisely. And it would do just like what we did. It would sample where you didn't sample before, effectively. So this is just to give you a sense of what's going on graphically when you optimize and spend a new budget. So this picture, the one on the left, the red profile corresponds to some existing profile of sampling that you had up to this point. That means some labels that were sampled at some point in time, and now you have some more budget to spend. So you want to get a better measurement on your items, which is the blue. The blue sort of profile is the new budget that you can spend. So what happens is what you expect. So you start spending your budget where the probability were smaller. So on the right side where there was actually nothing sampled. And then as you spend more budget, you're gonna first sample where you have the valleys, so that you have to sample less before. And eventually, if you spend enough money, you end up with an effective sampling profile which is uniform, which is what you want. Effectively, if you have enough budget, in the case of accuracy, you want to go back to a uniform sampling, and so you revert to that. Okay? So which is natural. Now, the last things that I want to mention about this is that to make things simpler, I'm talking about classification and accuracy, but all of this framework can work very naturally, not just for classification, but for supervised learning in general. So anytime you have labels, this can work. And so it doesn't just work for accuracy, it works for a whole range of different metrics. And you can also factor in sort of the posterior of your model to do sampling in a even smarter way. So for example, it makes sense, even in classification with accuracy, not to sample uniformly if you know ahead of time that your model is, for example, weaker in certain areas, so it's more likely that you make mistakes in certain areas, so you're going to sample harder there. So that can be included in this kind of framework. And finally, this kind of approach has a parallel in active learning, so on the training part. So again, keeping track of the sampling profile can help in training, for example, to remove the bias of your sampling when you did the training. And it goes very well hand in hand with active learning, where the sampling might not have been done uniformly on your set. Okay. That's all I had. If there are any questions, I'll be happy to answer. I think I have 3 minutes. Totally shocked. Too simple. Yes?
How many samples or how many items do you have to sample?
Sorry?
How many items do you have to sample?
You can look at the Walmart catalog. That's in the millions. I mean, this doesn't all just apply to the Walmart product catalog, but yes, where you, for example, one example of using this could be in our catalog of products. So Walmart has millions of products. So could be more, could be less. I mean. Yes? So the question is, if I understand, what if the classes changes and
What if the content you're classifying is changing? So the label is the same, but the distribution in the class change over time.
I'm not sure if this is answering your question, but one of the challenges, for example, yes, also not only the data changes, but also your taxonomy changes, right? So certain labels are going away, new ones are added. So yes, it works even there. The reason is, so if labels are going away, so effectively you're losing that data. So you will revert back to having zero probability on those items. But then when you sample again to get the new profile, you can you basically include those items to be sampled again, and the thing will take care of itself. And that actually is actually pretty common. I didn't talk about that, but it's actually one other major problem in this kind of. Yes? If the item that you're adding is the same as, sorry. Oh yeah, so you're touching on the problem of what we call variance. So yes, in retail, products, you can have a group of products that changes, for example, in size and color, but from the perspective of classification, they are the same products because they're all chairs, they're all, whatever, shirts. And so actually what we do is it's a pre-processing where we try to remove that redundancy. So we measure not the individual item, but the group of items that share the different sizes and the different colors. I don't know if that answers your question. The other aspect of this is that, as I said before, if, for example, you have an item that is similar, right? Your model might be telling you that you're pretty sure you're going to sample, that you know the answer for that, because it's very similar to something that you do have. So in that case, this kind of framework can factor in that information. So you can tell it to sample less things that are very likely, for which you're very likely to get the right answer. So roughly speaking, if you're close to the boundary, in your classifier, you probably want to sample more there than when you're very far off, when you most likely get it right. And that happens especially if you have a lot of products that are very similar and you really have tons of data around them. That's probably the case, and you're going to sample less those items.